Let's chat about the rank of a matrix. We say that if A is an M by N matrix, the rank of A, denoted rank A, is the rank of the operator that is left multiplication by A, that goes from Fn to Fm. Remember, LA of something that has sort of A1 through AN is defined to be A11 through A1N, AMN, AM1, AMN times A1 to AN, which is going to be a vector of dimension M, right? So let's just do a quick example of something like that. So LA here is going from R2 to R2, right? And so if we're concerned about the rank of this, we're concerned about the rank of this left multiplication. Remember, rank is the dimension of the range of this map, right? So let's just pick a basis of a basis of F2. 1, 0, 0, 1, right? So there's sort of the canonical basis. If I did LA applied to 1, 0, that's 1, 2, 3, 4, 1, 0, which gives me 1, 3, right? And what's LA of 0, 1? Right, that's somehow the second column vector. 2, 4, right? So the span of 1, 3, 2, 4, that's the range of the LA operator, right? So what is the span of those? Well, let's see. So you've got to think, well, what in F2 could I hit with vectors of those forms? Well, let's see. So what's the rank of that? So are these linearly independent, in which case the rank of this would be 2, this would be a basis, or are these linearly dependent? Well, suppose A 1, 2, 1, 3 plus B 2, 4 was equal to 0, 0, 0, I guess I should say. What's that mean? Meaning A plus 2B equals 0, and 3A plus 4B equals 0. But if you had these two things, right, you could multiply this first one by 2, or let's multiply by -2. So -2A minus 4B equals 0, and 3A plus 4B equals 0. That means that A equals 0, and if A equals B 0, then 0 plus 2B equals 0, and B equals 0. Therefore, the set 1, 3 and the set 2, 4 are linearly independent. Therefore, the rank of LA equals 2. So the rank of A equals 2, right? That's what we're talking about. Notice this somehow has everything to do with the fact that the columns of A are linearly independent. There are 2 columns and they're linearly independent. So let's look at this theorem. Let T from V to W be a linear transformation between finite dimensional vector spaces, and let beta and gamma be ordered bases of V and W respectively. So beta's in here, gamma's in there. The rank of T equals the rank of the matrix representation of T going from beta to gamma. But if you look back at homework number 20 in section 2.4, really 2.4 number 20, it actually says exactly this. It says this matrix, the rank of that left multiplication by this, right? So what is that defined to be? That's defined to be the rank of L of this matrix, right? So by definition, it's that. And this homework problem showed that these were the same. So the rank of the linear transformation and the rank of left multiplication by that matrix are the same. So that's really helpful. Okay, now, what do we do there? Now we've sort of reduced thinking about linear transformations and the rank, the dimension of the ranges, to thinking about them in terms of the rank of a matrix, okay? Now matrices have a lot of pluses. They're sort of very concrete and work the same way for every linear transformation. Whereas linear transformations might have different domains, matrices are all the same. So if you have a matrix A, an m by n matrix, and you have 2 invertible matrices, P an m by m invertible matrix and Q an n by n invertible matrix, so that P can be multiplied on the left of A and Q can be multiplied on the right, then the rank of AQ equals the rank of A, and the rank of PA equals the rank of A. And so obviously if these two happen, then this is sort of a direct consequence. Just sort of think about P of AQ being the rank of PQ, of AQ, and then use the other piece. So C follows immediately from A and B. And A and B sort of, if you think about this, the proof of A, well, what's true about the range of left multiplication by AQ, right? And remember, of course, this is defined to be the dimension of the rank of that map. Well, that's just the range of L left multiplication by A left multiplication by Q. And, what is that? You could just define that on sets like this, right? But then, well, what is this? This is an invertible matrix, right? So by definition, it's onto. So that's just LA Fn. And what's that? Using that same somehow fact to get back, that's the range of the map LA. And that's really the definition of the right-hand side, okay? Think about this left-hand side, part B, as follows. LA, okay, think about this. LA is, you have the dimension of the range of LA, that by definition is the rank here, right, is the dimension of LP applied to the range of LA. Right, these are really the same thing, right, since this is invertible, which is the dimension of LP LA of the base field, right? Let me make sure that that's the right piece there. I think to go on the input there, it has to be N, sorry. Okay, well, but think about this. What is that? That's just LPA on Fn, which is just the dimension of the range of LPA. So in some ways, it's just thinking about what those pieces are, right? Okay, so there is one corollary that is worth mentioning before we wrap this up, and the corollary goes something like this, or exactly like this. Elementary row and column operations on a matrix are rank preserving. And why is it a corollary? Because elementary row and column operations correspond to multiplication by elementary matrices, right? Row operations correspond to multiplication on the left, column operations correspond to multiplication on the right, and the theorem says that if you're multiplying by an invertible matrix, right? And of course, theorem 3.2 says these are invertible, all elementary matrices are invertible. Well, then you have exactly what the theorem said, which is multiplication on the left or on the right by an invertible matrix, in this case an elementary matrix, is rank preserving.